In the vast expanse of the Milky Way galaxy, amidst a swirling ocean of stars and interstellar clouds, a delicate sequence of events set the stage for the birth of Earth. Roughly 4.6 billion years ago, the galaxy was home to regions dense with gas and dust, remnants of ancient stars that had lived and died in spectacular supernovae. These violent explosions scattered the essential elements of planet formation: carbon, silicon, iron, and more, throughout space, seeding the cosmos with the building blocks of planets like Earth. Within one such region, a cloud of gas and dust began to collapse under its own gravity. This collapse was likely triggered by the shock wave of a nearby supernova, compressing the cloud and initiating the slow dance of planetary creation. As the cloud contracted, it began to spin, flattening into a disk with the densest material accumulating at its center. This was the nascent solar system, a dynamic and chaotic environment where dust grains collided, clumped together, and eventually grew into larger bodies. At the heart of this swirling disk, immense pressure and heat ignited nuclear fusion, giving birth to the Sun. Its intense gravity and radiant energy dominated the surrounding space, influencing the behavior of the material in the protoplanetary disk. Over time, regions within the disk differentiated, with temperature gradients dictating where various materials could condense. Closer to the Sun, where it was hotter, only metals and silicates could form solids, while farther out, ices and gases remained stable. In this inner region, rocky worlds began to take shape, including the planet that would one day become Earth. Small particles collided and stuck together, forming pebble-sized aggregates. These aggregates grew into larger bodies called planetesimals, the foundational pieces of planets. The early solar system was a tumultuous place, with collisions between planetesimals frequently merging them into larger, embryonic planets. Earth's growth was steady, but marked by violent impacts. As a planetesimal grew, its increasing mass allowed it to pull in more material through its gravitational influence. Over millions of years, it became a protoplanet, a chaotic sphere of molten rock shaped by relentless collisions. Each impact contributed to Earth's evolution, adding mass and heat to its already turbulent state. One of these collisions was particularly significant: the impact with Theia, a Mars-sized body, which would later create the Moon, a pivotal moment in Earth's history. The differentiation of elements began during this molten phase. Heavier materials like iron and nickel sank to the center, forming Earth's dense core. Lighter silicates rose to the surface, creating the mantle and the beginnings of a crust. This internal layering set the foundation for Earth's magnetic field, tectonic activity, and the eventual stabilization of its surface. Utilizing tectonic pulse and crashes along the way, the ether composition produced the most magnetic field, The early solar system's environment also played a crucial role in Earth's formation. The gravitational influence of the giant planets, particularly Jupiter, shaped the distribution of materials within the protoplanetary disk. Jupiter's migration inward and subsequently retreat outward cleared vast swaths of debris, funneling material into the inner solar system and influencing the trajectories of planetesimals. While Jupiter's presence prevented the formation of a super-Earth closer to the Sun, it allowed Earth to form without competition from larger planets, giving it the opportunity to grow steadily in size and stability. By the time Earth had fully formed, it was one of 4 rocky planets in the inner solar system, joined by Mercury, Venus, and Mars. Each of these worlds shared a similar origin, yet Earth stood out. Its size, composition, and distance from the Sun created conditions that set it apart as a unique planetary body. Though it would take billions of years for Earth to evolve into the vibrant blue sphere we recognize today, the seeds of its uniqueness were planted during its cosmic birth. The origins of Earth are a testament to the delicate interplay of cosmic forces, from the explosion of ancient stars to the swirling chaos of a protoplanetary disk. Earth's creation was shaped by events on both grand and microscopic scales. These beginnings, though violent and chaotic, lay the groundwork for a planet that would one day stand as a singular marvel in the vastness of space. The young Earth was a planet born in fire, a hostile sphere of molten rock and turbulent activity. In its earliest days, the proto-Earth was little more than a chaotic mass of molten material, its surface glowing red from the heat of constant collisions. The energy released by the accretion of planetesimals, combined with the decay of radioactive elements within its interior, generated temperatures so extreme that no solid crust could form. The Earth we now know was unrecognizable in this state, a fiery, formless world shaped by the violence of its birth. The surface of early Earth was a vast ocean of magma, with temperatures reaching thousands of degrees Celsius. This searing heat caused heavy materials like iron and nickel to sink toward the core, while lighter silicates floated upward. This process, known as planetary differentiation, created Earth's distinct internal layers, a dense metallic core at its center, surrounded by a semi-fluid mantle and an unstable outer crust that would take millions of years to solidify. This layering was a defining moment, giving Earth the structural foundation for its future development. Bombardment from the remnants of the protoplanetary disk continued to shape the young planet. Asteroids and comets pummeled the surface, adding to the chaos. Each impact released tremendous energy, melting and vaporizing vast portions of Earth's crust. Some of these collisions brought critical elements, including volatile compounds like water, carbon, and nitrogen, which would later play a role in forming the planet's oceans and atmosphere. Something like it, however, in this molten state, Earth was far from being a hospitable home for life, or even a stable planetary body. The Earth's molten interior also fueled intense volcanic activity. Massive eruptions spewed gases into the atmosphere, including carbon dioxide, water vapor, and sulfur compounds. These volcanic emissions helped form Earth's first atmosphere, though it was vastly different from the one we breathe today. This primordial atmosphere lacked oxygen and was instead dominated by greenhouse gases, trapping heat and further preventing the planet from cooling quickly. Over time, the balance between volcanic activity and heat loss to space began to shift, allowing a thin, fragile crust to form intermittently over the molten mantle. Extract from comparative manner. Despite the relentless heat and bombardment, these early processes were essential for Earth's evolution. Differentiation of the core and mantle set the stage for the planet's magnetic field, a protective barrier that would later shield Earth from the sun's solar wind. The accumulation of volatile materials laid the groundwork for the eventual development of oceans and weather systems. Even the chaotic bombardment contributed to Earth's growth, gradually increasing its mass and stabilizing its orbit. One of the most significant events during this fiery phase was the collision with Theia, a Mars-sized planetesimal. The impact was catastrophic, vaporizing much of Earth's crust and ejecting debris into orbit. This material coalesced into the Moon, a companion that would stabilize Earth's tilt and influenced its evolution for billions of years. Theia's impact also accelerated the differentiation of Earth's interior, further refining its composition. As the bombardment began to subside, Earth entered a period of gradual cooling. The magma ocean started to solidify, forming the first patches of solid crust. These proto-continents were small, unstable, and frequently recycled back into the molten mantle by ongoing volcanic activity and impacts. However, they represented the first steps toward a more stable planetary surface. As the specialized people who infiltrated water from the Earth's solar crust for hydrogen to be used had already formed a predominant position in the planet's floor at this point. The process of cooling and crust formation was slow and uneven, taking millions of years to establish the foundation of the planet's surface as we know it. During this time, the heat from Earth's interior remained intense, driving powerful convection currents in the mantle. These currents contributed to the movement of surface materials and set the stage for the later development of plate tectonics. Volcanic activity continued to reshape the surface, releasing gases that thickened the atmosphere and eventually helped retain heat in a more controlled manner. Though the fiery phase of Earth's history was far from over, the planet was slowly transitioning from a chaotic sphere of molten rock to a more defined and stable world. From a cosmic perspective, this fiery beginning was not unique to Earth. Other planets in the solar system, particularly the rocky worlds like Venus and Mars, experienced similar molten phases during their formation. However, Earth's size, composition, and distance from the Sun set it apart, allowing it to retain heat and volatile materials while also cooling at a rate conducive to long-term stability. This balance was crucial in shaping Earth into a planet capable of supporting the dynamic processes that define its identity today. Earth's early history as a molten world may seem harsh and uninviting, but it was a necessary stage in its journey. The fiery conditions allowed for the mixing and redistribution of materials, creating a planet with a differentiated interior, a thick atmosphere, and the potential for geological activity. These foundational characteristics would set the stage for Earth's transformation into a stable, water-rich world, a planet that, even in its earliest days, stood apart as a remarkable object in the solar system. Approximately 4.5 billion years ago, in the chaotic infancy of the solar system, Earth faced a cataclysmic event that would forever shape its future. A Mars-sized planetary body, now referred to as Theia, collided with the young Earth. This collision was not a mere impact. It was a titanic event, unleashing energy so immense that it reshaped both worlds. From the debris of this violent encounter, the Moon was born, becoming Earth's constant companion and an integral part of its evolution. Theia likely formed in a nearby orbit to Earth, a fellow traveler in the inner solar system. Over time, gravitational interactions between Theia and Earth destabilized Theia's orbit, setting it on a collision course. When the two bodies finally met, the impact occurred at a glancing angle rather than head-on. This oblique strike caused a significant portion of Earth's outer layers to be ejected into space, while leaving Earth's core largely intact. The aftermath of the collision was a scene of extraordinary chaos. Vaporized rock and molten debris were hurled into orbit, forming a ring around Earth. Within this ring, the particles began to coalesce, drawn together by their mutual gravity. Over tens of millions of years, these fragments formed a single solid body, the Moon. Its formation was relatively rapid in cosmic terms, marking one of the defining events in Earth's history. The impact also had profound effects on Earth itself. The collision tilted Earth's axis, giving the planet its characteristic 23.5-degree tilt. This tilt introduced the concept of seasons, as different parts of the planet would receive varying amounts of sunlight throughout the year. Without this axial tilt, Earth might have experienced a monotonous climate, lacking the diversity that defines its weather patterns today. In the immediate aftermath of the collision, Earth was a violent and molten world, surrounded by a newly formed moon that orbited much closer than it does today. The gravitational interaction between Earth and the moon was intense, causing tidal forces that reshaped Earth's surface and accelerated its rotation. Early Earth days were as short as 6 hours, a rapid spin that would gradually slow over billions of years due to the moon's influence. The moon's gravitational pull also played a critical role in stabilizing Earth's axial tilt. Unlike Mars, which experiences wild variations in its axial tilt over time, Earth's tilt has remained relatively constant. This stability has been crucial for maintaining a predictable climate and fostering long-term geological and atmospheric processes. Without the Moon, Earth's tilt might have fluctuated chaotically, potentially preventing the development of the stable conditions that define the planet today. The Moon's formation also accelerated the differentiation of Earth's interior. The immense heat generated by the collision caused the planet to remain in a molten state for an extended period, allowing heavy elements to sink deeper into the core and lighter materials to rise toward the surface. This layering process was vital in forming Earth's magnetic field. The collision also added new material to Earth's crust, altering its composition and enriching it with lighter elements. From a space perspective, the Moon's presence creates a striking contrast with Earth. Its barren, cratered surface tells the story of countless impacts that Earth likely shared but has since erased through erosion and geological activity. The Moon serves as a historical archive of the solar system's early days, providing valuable insights into the conditions that shaped Earth and its neighbors. The Moon's gradual retreat from Earth, at a rate of about 3.8 centimeters per year, is another legacy of the collision. As the Moon moves farther away, its gravitational influence on Earth diminishes. Over billions of years, this retreat will lengthen Earth's days and reduce the intensity of tides, subtly altering the dynamics of the planet. While other moons exist throughout the solar system, none share the unique relationship that Earth and its moon have. The Moon's size relative to Earth is unusually large, creating a balance that stabilizes the planet's tilt and moderates its tidal forces. This relationship is a direct result of their shared origin in the aftermath of Thea's impact. The collision that created the Moon was a moment of profound transformation for Earth. It reshaped the planet's interior, established its axial tilt, and introduced a celestial companion that would influence its evolution for billions of years. The Moon stands as a testament to the violent beginnings of the solar system, a silent witness to its ongoing journey through space. Earth occupies a unique and fortunate position within the solar system, nestled in what scientists often call the habitable zone, or the Goldilocks zone. This is the region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. For Earth, this placement has been one of the defining factors in its evolution as a dynamic and enduring planetary body. Located roughly 150 million kilometers, 93 million miles from the Sun, Earth resides at a distance where solar radiation provides the energy needed to sustain a moderate surface temperature. This equilibrium ensures that water, one of the most vital components of Earth's systems, remains in liquid form for much of the planet's history. Planets closer to the Sun, like Venus, experience extreme heat that causes water to evaporate, while those farther out, like Mars, face temperatures too cold to support sustained liquid water. Earth's nearly circular orbit around the Sun also contributes to its stability. With an orbital eccentricity that is very low, Earth avoids dramatic swings in distance from the Sun, ensuring that the amount of solar energy it receives remains relatively constant. This consistency is crucial in preventing extreme climatic variations that could disrupt the planet's systems. In contrast, planets with more elliptical orbits, such as Mercury, experience significant temperature fluctuations as they move closer to and farther from the Sun. The Sun itself plays a pivotal role in Earth's position and long-term stability. As a middle-aged, relatively stable GTP main sequence star, the Sun provides a steady output of energy. Unlike younger stars that are prone to violent flares, or older stars nearing the end of their life cycle, the Sun has remained predictable for billions of years, allowing Earth's systems to evolve under stable conditions. This reliability is a key factor in Earth's long-term habitability as a planet. The gravitational interactions between Earth and its neighboring planets further reinforce its position in the solar system. Jupiter, the largest planet, exerts a strong gravitational pull that helps stabilize the inner solar system. By capturing and redirecting comets and asteroids, Jupiter acts as a cosmic shield, reducing the frequency of catastrophic impacts on Earth. At the same time, Venus and Mars, Earth's closest rocky neighbors, have subtly influenced Earth's orbit over time through gravitational resonances, contributing to its long-term stability. Earth's size and mass also play a significant role in maintaining its position and character as a planet. At approximately 1.274 kilometers, 7,918 miles, in diameter, Earth is large enough to retain a substantial atmosphere, yet not so massive that it would trap lighter gases like hydrogen and helium, which dominate the atmospheres of gas giants. This balance has allowed Earth to sustain an atmosphere rich in nitrogen, oxygen, and trace gases, key components for its dynamic systems. From its vantage point in the inner solar system, Earth is part of the quartet of rocky planets: Mercury, Venus, Earth, and Mars. These terrestrial planets are characterized by their solid surfaces, in contrast to the gas giants farther out. Earth's size and density make it the largest and most geological activity of these inner planets. Its ability to sustain tectonic activity, a thick atmosphere, and a magnetic field sets it apart from its rocky companions. The planet's relationship with the Sun extends beyond the energy it receives. Solar radiation interacts with Earth's magnetic field and atmosphere, driving phenomena like the auroras and influencing climate patterns. Earth's orbit also creates predictable cycles, such as the 24-hour day and the annual year, which are foundation to the rhythms of the planet's systems. Variations in the planet's orbit, axial tilt, and precession over tens of thousands of years, known as Milankovitch cycles, have driven long-term climate shifts, including ice ages. Despite Earth's favorable position in the solar system, it is not immune to external influences. Occasional perturbations from other celestial bodies, such as passing asteroids or comets, remind us of the dynamic nature of the solar system. However, Earth's placement in a relatively uncrowded region, combined with its interactions with larger planetary bodies, minimizes the risks of frequent catastrophic events. Viewed from space, Earth's position in the solar system is a delicate balance of distance, size, and timing. It orbits at the right distance from the Sun to sustain liquid water, in a stable orbit that avoids dramatic fluctuations in climate. It shares its space with neighbors that, while vastly different in their characteristics, contribute to its overall stability through gravitational interactions. This balance has allowed Earth to evolve as a planet with dynamic systems, a thick atmosphere, and the capacity to endure over billions of years. Earth's location in the solar system is not just a matter of coincidence, but the result of countless interconnected factors, from the Sun's energy output to the gravitational choreography of the planets. Every element contributes to the planet's unique identity. This position has shaped Earth's history, defining its role as a vibrant, active world in a dynamic celestial neighborhood. One of Earth's most defining characteristics as a planet is its abundance of liquid water, a feature unmatched in the solar system. However, Earth wasn't always a blue planet. In its earliest days, Earth was a fiery and desolate world, where surface water could not exist due to intense heat and volcanic activity. The arrival and retention of water marked a pivotal moment in Earth's evolution, transforming it into a planet dominated by oceans and shaping its surface, atmosphere, and long-term stability. Water likely arrived on Earth through multiple processes, beginning with the heavy bombardment of asteroids and comets during the solar system's chaotic early history. These objects, remnants of the protoplanetary disk, carried significant amounts of ice and volatile compounds, including water. When they collided with the molten surface of the young Earth, the ice vaporized, and the water vapor was released into the atmosphere. Over time, as Earth began to cool, this vapor condensed, forming clouds and eventually precipitating as rain, which filled the basins that became the planet's first oceans. Fish started to swim aboard, and soon the whole planet saw an emerging kind of life, starting with animals, the moon, and plants. The late heavy bombardment, a period of intensified asteroid and comet impacts approximately 4 billion years ago, played a crucial role in delivering water to Earth. During this time, the solar system's giant planets, particularly Jupiter and Saturn, underwent orbital shifts, destabilizing nearby asteroid belts and sending countless rocky and icy bodies toward the inner solar system. Earth, as one of the larger targets, absorbed many of these impacts, accumulating vast amounts of water and other volatile materials in the process. Volcanic activity on early Earth also contributed to the accumulation of water. As molten rock erupted from the planet's interior, it released water vapor trapped within the magma. This outgassing process added to the growing atmospheric reservoir of water vapor, which eventually cycled back to the surface through precipitation. Volcanic outgassing was a critical mechanism, ensuring a continuous supply of water even after the initial influx from space had slowed. Earth's unique ability to retain water is closely tied to its size and gravity. Unlike smaller bodies, such as the Moon or Mars, Earth's gravitational pull is strong enough to hold on to water molecules. Additionally, Earth's magnetic field, generated by its molten core, protects its atmosphere from being stripped away by the sun's solar wind. This shield ensures that water, once delivered, remains on the planet over geological timescales. By the time Earth cooled sufficiently for its surface to solidify, water began to accumulate in low-lying regions, forming the first oceans. These oceans covered a significant portion of the planet, creating a dynamic water cycle that included evaporation, condensation, and precipitation. The movement of water across Earth's surface and through its atmosphere established the foundation for weather systems, erosion, and the transport of nutrients, all of which would later play crucial roles in shaping the planet's geology and climate. The presence of liquid water also influenced the development of Earth's crust. Oceanic plates, formed under the weight of accumulating water, became a defining feature of Earth's surface. These plates facilitated the onset of plate tectonics, a process unique among the rocky planets. Water's ability to weaken rocks and lubricate faults made it an essential component of tectonic movement, allowing Earth's crust to recycle and renew itself over time. While Earth retained most of its water, some was lost to space, particularly in its early history. Solar radiation and interactions in the upper atmosphere caused lightweight hydrogen atoms to escape into space, breaking apart water molecules in the process. However, Earth's size, gravity, and magnetic field minimized these losses, ensuring that the planet remained water-rich compared to its neighbors. From space, Earth's transformation into a water world is striking. The planet's oceans reflect sunlight, giving it its characteristic blue appearance. These vast bodies of water cover nearly 71% of Earth's surface, with depths averaging 3.7 kilometers, 2.3 miles. The oceans play a critical role in regulating the planet's climate and maintaining a stable environment. Water's presence is not evenly distributed across the solar system, making Earth's abundance even more remarkable. Venus, Earth's closest planetary neighbor, may have once harbored water, but lost it due to a runaway greenhouse effect and intense solar radiation. Mars, on the other hand, retains traces of water ice at its poles and beneath its surface, but lacks the atmosphere and gravity needed to sustain liquid water over long periods. In contrast, Earth's unique combination of distance from the sun, size, and magnetic protection has allowed it to sustain its water cycle for billions of years. The arrival and retention of water on Earth was a transformative event, marking the transition from a volatile molten world to a planet capable of dynamic processes. The oceans not only shaped Earth's surface, but also played a key role in regulating its atmosphere and temperature. From the vast oceans to the intricate water cycle, water is central to Earth's identity as a planetary body, setting it apart as a vibrant, evolving world in the solar system. Earth's atmosphere is one of its most defining features, providing a protective envelope that moderates temperature, shields the surface from harmful radiation, and facilitates the dynamic processes that have shaped the planet over billions of years. However, this atmosphere did not exist in its present form when Earth first formed. Its evolution was a gradual and complex process, influenced by volcanic activity, chemical reactions, and interactions with the Sun. When Earth initially coalesced from the dust and debris of the protoplanetary disk, it was surrounded by a thin veil of hydrogen and helium, the lightest and most abundant elements in the universe. This was Earth's first atmosphere, inherited from the primordial solar system. However, this atmosphere was short-lived. The young Sun, more active and volatile than it is today, emitted intense solar winds and bursts of radiation. Earth's gravity, though significant, was not strong enough to retain these lightweight gases against the onslaught of solar wind. Within a few million years, the first atmosphere was stripped away, leaving Earth barren. As Earth's interior differentiated and volcanic activity became a dominant force, the planet began to generate a secondary atmosphere. Volcanic eruptions released vast amounts of gases trapped within the molten interior, a process known as outgassing. This included water vapor, carbon dioxide, sulfur dioxide, nitrogen, and trace amounts of other gases. The atmosphere that emerged was thick and dominated by greenhouse gases, with no free oxygen. These volcanic emissions were critical in creating the building blocks of a more stable atmosphere. Water vapor from volcanic outgassing played a particularly important role. As Earth cooled and the first oceans formed, much of the water vapor condensed and returned to the surface as liquid, leaving behind a denser atmosphere primarily composed of carbon dioxide and nitrogen. These gases trapped heat, keeping Earth's surface warm despite the fanging sun, whose energy output was much weaker than it is today. This greenhouse effect was essential in maintaining surface temperatures above freezing during Earth's early history. The interaction between the oceans and the atmosphere began to regulate the composition of the atmosphere over time. Carbon dioxide, which had initially dominated, was gradually drawn down by chemical weathering and dissolved into the oceans. There, it reacted with minerals to form carbonate compounds, effectively locking away significant amounts of CO2 in rocks and sediments. This process, combined with ongoing volcanic activity, established a long-term carbon cycle that would continue to influence Earth's atmosphere for billions of years. An explanation was given for existing continents on the planet. Earth's magnetic field also played a pivotal role in protecting its atmosphere. Generated by convection currents in the molten iron core, the magnetic field deflected charged particles from the sun, preventing the solar wind from eroding the atmosphere. This protection was vital in allowing Earth to retain its atmosphere, while other planets, such as Mars, lost much of theirs due to the absence of a magnetic shield. Unlike Venus, where a runaway greenhouse effect caused CO2 to dominate the atmosphere, Earth's ability to regulate its atmospheric composition through geological and chemical processes created a more balanced environment. However, Earth's early atmosphere remained harsh and unbreathable. With no oxygen, it resembled the atmospheres of Venus or Titan, rich in nitrogen, methane, and sulfur compounds, and it supported extreme heat due to the high concentration of greenhouse gases, he said. The absence of free oxygen in the early atmosphere is a defining characteristic of this stage in Earth's history. Oxygen would not become a significant part of the atmosphere until billions of years later, following the emergence of photosynthetic organisms. However, even in its oxygen-free state, the atmosphere was thick and dynamic, shaping Earth's surface through processes like weathering, precipitation, and erosion. Viewed from space, Earth's early atmosphere likely appeared as a dense, hazy envelope surrounding a molten, volatile planet. Thick clouds of sulfur and carbon dioxide obscured the surface, while volcanic eruptions continuously fed gases into the atmosphere. Lightning storms, fueled by the abundance of charged particles, were frequent, adding to the planet's dynamic character. Over time, Earth's atmosphere continued to evolve, becoming less dominated by carbon dioxide as the oceans absorbed and sequestered it. Nitrogen, released during volcanic outgassing and largely inert, became the dominant gas. This atmospheric transformation marked a transition to a more stable and enduring environment, paving the way for the complex systems that would define Earth in later eras. Earth's atmosphere, in its various stages, has always been a reflection of the planet's internal and external processes. From its volatile beginnings as a hydrogen-rich haze to its current balanced state, it is a dynamic system shaped by volcanic activity, solar interactions, and chemical cycles. This transformative journey highlights Earth's resilience and adaptability, setting it apart as a unique planetary body in the solar system. Among Earth's most critical and least visible features is its magnetic field, a protective force generated by the planet's molten iron core. This field, often called the magnetosphere, extends far into space and serves as Earth's first line of defense against the relentless onslaught of solar winds and cosmic radiation. Without it, Earth's atmosphere and surface would be vulnerable to the destructive forces of space, making the planet far less hospitable and stable. The magnetic field originates deep within Earth's interior. At the heart of the planet lies a solid inner core, composed primarily of iron and nickel, surrounded by a molten outer core. The difference in temperature and composition between these layers drives convection currents in the liquid outer core. As the molten iron moves, it generates electric currents, which in turn produce magnetic fields. This process, known as the geodynamo, sustains Earth's magnetic field, and has done so for billions of years. The magnetic field itself takes the shape of a dipole, similar to a bar magnet, with magnetic poles near Earth's geographic north and south poles. However, the field is far from static. It is dynamic and constantly shifting. Over geological timescales, the magnetic poles have reversed numerous times, a phenomenon known as a geomagnetic reversal. These reversals, while seemingly chaotic, do not disrupt the overall protective function of the magnetosphere. The magnetosphere is vast, stretching tens of thousands of kilometers into space. It forms a protective bubble around the planet, deflecting charged particles from the sun, known as the solar wind. These high-energy particles could otherwise strip away Earth's atmosphere, as they have on Mars, a planet that lacks a strong magnetic field. The magnetosphere's role in preserving Earth's atmosphere has been crucial in maintaining the planet's ability to sustain water and a stable climate. When solar wind particles collide with Earth's magnetosphere, they are guided along magnetic field lines toward the poles. There they interact with molecules in the upper atmosphere, creating the dazzling displays known as auroras. These natural light shows, visible near the Arctic and Antarctic circles, are a beautiful reminder of the magnetic field's invisible presence and its interaction with cosmic forces. The strength and stability of Earth's magnetic field are directly tied to the dynamics of its core. As the core gradually cools over billions of years, the geodynamic process will eventually weaken, reducing the strength of the magnetic field. When this happens, potentially billions of years from now, Earth will lose much of its protection from solar and cosmic radiation, leading to significant atmospheric loss and increased exposure to harmful space weather. The magnetic field has also played a key role in shaping Earth's surface and geological history. By shielding the planet from excessive radiation, it has helped to preserve the delicate balance of atmospheric gases necessary for maintaining a stable climate. Additionally, the magnetic field protects technological systems on Earth, such as satellites and power grids, from disruptions caused by solar storms. Earth's magnetic field is not only vital for the planet's current stability, but also serves as a historical record of its geological past. Magnetic minerals in rocks align with the field as they form, preserving a snapshot of the magnetic field's direction and strength at the time. These fossilized magnetic signatures have allowed scientists to reconstruct the history of geomagnetic reversals and the movement of tectonic plates over millions of years. From a space perspective, the magnetosphere is a striking feature. Observations from satellites and probes reveal its teardrop-shaped structure, with a compressed side facing the sun and a long tail stretching away from it. This shape results from the interaction between the solar wind and the magnetic field, creating a dynamic boundary known as the magnetic field. Beyond this boundary lies the interplanetary space, where the influence of the sun's magnetic field dominates. Comparatively, Earth's magnetic field sets it apart from its neighbors. Venus, despite its similar size and composition, lacks a magnetic field, leaving its atmosphere vulnerable to solar winds. Mars, with its small and solid core, has only localized magnetic anomalies and no global field, contributing to the loss of much of its atmosphere over time. In contrast, Earth's robust magnetosphere has ensured the long-term preservation of its atmosphere and surface conditions. The magnetic field is an unsung hero of Earth's stability, an invisible force that has shaped the planet's past and safeguards its future. Its dynamic interactions with the sun and space weather demonstrate the interconnectedness of Earth's systems with the wider cosmos. Though unseen by the naked eye, the magnetic field is a constant, silent guardian, ensuring that Earth remains a resilient and thriving planet within the solar system. One of the most remarkable features of Earth, as observed from space and studied on the ground, is its ever-changing surface. Unlike the static landscapes of other rocky planets, Earth's surface is in constant motion, driven by the powerful forces of plate tectonics. This dynamic system, unique among the terrestrial planets, is responsible for the formation of continents, mountains, ocean basins, and the recycling of the planet's crust. Plate tectonics is central to Earth's identity as an active and evolving planetary body. Earth's lithosphere, the rigid outer shell of the planet, is broken into several large and small pieces called tectonic plates. These plates float on the more ductile asthenosphere, a layer of the mantle that flows over geological timescales. The movement of tectonic plates is driven by convection currents in Earth's mantle, caused by heat escaping from the planet's interior. These currents create a cycle of rising and sinking material that exerts forces on the plates above, pushing them apart, pulling them together, or causing them to slide past one another. The boundaries between tectonic plates are regions of intense geological activity. At divergent boundaries, such as the Mid-Atlantic Ridge, plates move apart, allowing magma from the mantle to rise and solidify, forming new crust. This process, known as sea floor spreading, continuously renews the oceanic crust. In contrast, at convergent boundaries, plates collide, and one plate is forced beneath the other in a process called subduction. Subduction zones are sites of volcanic activity and the formation of mountain ranges, such as the Andes in South America. At transform boundaries, plates slide past each other, creating faults like the San Andreas Fault in California, where earthquakes are common. Plate tectonics plays a crucial role in regulating Earth's internal heat. As plates move, they transport heat from the planet's interior to the surface, where it is released through volcanic eruptions and mid-ocean ridges. This heat transfer prevents Earth's interior from becoming excessively hot and contributes to the dynamic nature of the surface. From space, the effects of tectonic activity are visible in the patterns of mountain ranges, rift valleys, and ocean trenches that span the planet. Features such as the Himalayas, formed by the collision of the Indian and Eurasian plates, and the Pacific Ring of Fire, a chain of volcanoes and seismic activity surrounding the Pacific Ocean, showcase the global scale of tectonic forces. These features highlight Earth's status as a geologically active world, in contrast to planets like Mars and Mercury, where tectonic activity ceased long ago. Earth's tectonic processes are also deeply interconnected with its atmosphere and hydrosphere. Subduction zones play a key role in the carbon cycle, as carbonate-rich sediments are dragged into the mantle, where they release CO2 through volcanic activity. This cycling of carbon between the surface and interior helps regulate Earth's climate over long timescales. Additionally, tectonic activity contributes to the formation of landscapes that influence weather patterns and the distribution of ecosystems. The presence of liquid water is a critical factor in Earth's active tectonics. Water weakens rocks and lowers the melting point of minerals, facilitating the movement of tectonic plates. It also acts as a lubricant in subduction zones, allowing one plate to slide beneath another more easily. This interplay between water and tectonics is unique to Earth and has no known parallel on other rocky planets. 8. While tectonic forces shape the surface, they also contribute to natural hazards. Earthquakes, volcanic eruptions, and tsunamis are all consequences of plate movements. These events remind us of the immense energy stored within the planet and the dynamic processes that continuously reshape its surface. Over billions of years, tectonic activity has driven the formation and breakup of supercontinents, such as Pangaea. These cycles of assembly and fragmentation, known as the supercontinent cycle, have profoundly influenced the planet's geology, climate, and even the evolution of its surface features. The creation of new crust at mid-ocean ridges and its destruction at subduction zones ensures that Earth's surface remains geologically fresh, in stark contrast to the ancient and heavily cratered landscapes of other planets. Earth's tectonic system is also responsible for its distinctive seismic activity. The constant shifting of plates creates stresses that build up and are eventually released as earthquakes. These seismic events provide valuable insights into the structure and dynamics of Earth's interior, as they generate waves that travel through the planet, revealing the composition and behavior of its core and mantle. Plate tectonics is a hallmark of Earth's uniqueness as a planetary body. It drives the creation and destruction of landforms, recycles materials between the surface and interior, and regulates the planet's interior heat. From the perspective of space, Earth's constantly shifting surface is a testament to its dynamic nature and sets it apart from other planets in the solar system. The ceaseless motion of Earth's plates is both a reminder of the planet's vibrant geology and a window into its deep history. Through tectonic forces, Earth remains an ever-evolving world, continuously reshaped by the powerful processes that began billions of years ago and continue to define its surface today. Earth's orbit and axial tilt are fundamental to its role as a dynamic and evolving planet. These orbital and rotational characteristics regulate the distribution of sunlight, drive the planet's climate systems, and ensure the stability of its environment over geological timescales. Together, they create the rhythms of days, seasons, and years that define Earth as a unique and enduring member of the solar system. Earth orbits the Sun at an average distance of about 150 million kilometers, 93 million miles, a position within the habitable zone, where conditions are favorable for liquid water to exist. This orbit is nearly circular, with an eccentricity of only about 0.167, meaning the distance between Earth and the Sun changes only slightly throughout the year. Lieutenant General Barclay, one of the world's greatest experts on space magic for passing, has compiled a list of the icons. The orbit is nearly slightly throughout the year. This low eccentricity minimizes temperature extremes, ensuring relatively stable climate conditions compared to planets with more elliptical orbits, such as Mars. The axial tilt of Earth, approximately 23.5 degrees relative to its orbital plane, is a defining feature of the planet's climate. This tilt, known as obliquity, is the reason Earth experiences seasons. As the planet orbits the Sun, its tilt causes different hemispheres to receive varying amounts of sunlight throughout the year. During the summer solstice in the northern hemisphere, the North Pole is tilted toward the sun, resulting in longer days and warmer temperatures. Inversely, during the winter solstice, the North Pole tilts away from the sun, leading to shorter days and colder weather. This alternating pattern ensures a diversity of climates and ecological cycles across the planet. The stability of Earth's axial tilt is largely due to the presence of the Moon. Without the Moon's gravitational influence, Earth's tilt would likely vary chaotically over time, as it does on Mars, which lacks a large natural satellite. Such variations could lead to dramatic climate swings, making Earth far less stable and hospitable. The Moon acts as a stabilizing force, ensuring that Earth's tilt remains within a narrow range, which has been crucial for maintaining a relatively predictable climate over millions of years. Earth's rotation, or the length of a day, is another essential aspect of its dynamics. Currently, a day on Earth lasts approximately 24 hours, but this was not always the case. Early in its history, Earth's days were much shorter, closer to 6 hours. Due to its rapid rotation, over billions of years, tidal interactions with the Moon have slowed Earth's rotation, gradually lengthening the day. This process, known as tidal braking, continues today, with Earth's rotation slowing by about 1.8 milliseconds per century. The interaction between Earth's rotation and its axial tilt gives rise to another phenomenon, the precession of the equinoxes. Precession refers to the slow wobble of Earth's rotational axis, which traces out a conical shape over a cycle of approximately 2,6,000 years. This gradual shift alters the alignment of the seasons over millennia. Precession is part of a larger set of orbital variations, known as Milankovitch cycles, that also include changes in Earth's eccentricity and axial tilt. These cycles influence long-term climate patterns, including the timing of ice ages. From a space perspective, Earth's orbit creates a striking image of balance and harmony. The planet's nearly circular path ensures that it remains at a consistent distance from the Sun, receiving a stable influx of solar energy. The tilt of the planet is evident in the distribution of sunlight across its surface, with the polar regions receiving less energy and the equatorial regions receiving more. This uneven heating drives atmospheric and oceanic circulation, creating the complex systems that regulate Earth's climate. The transition between night and day, as seen from space, is another remarkable feature of Earth's rotation. The line dividing day and night, known as the terminator, sweeps across the planet's surface every 24 hours. This rapid alternation between light and darkness is a direct result of Earth's rotation and underscores the planet's dynamic interaction with the Sun. Earth's orbital velocity, averaging about 29.78 kilometers per second, 18.5 miles per second, ensures it completes one revolution around the Sun every 365.25 days. This slight fraction of a day necessitates the addition of a leap day every 4 years to keep the calendar aligned with Earth's orbit. These orbital mechanics are not just astronomical curiosities. They are the foundation of human timekeeping and our understanding of the planet's position in the cosmos. Over geological timescales, Earth's orbit and rotation have undergone gradual changes due to gravitational interactions with other planets and the Sun's evolving energy output. While these changes are subtle, they have profound effects on Earth's climate and environment. For example, slight shifts in the planet's orbit and tilt have been linked to the onset and retreat of ice ages, demonstrating the interconnectedness of Earth's orbital dynamics and its surface conditions. Earth's orbit and axial tilt are a delicate balance of celestial mechanics shaped by the planet's interactions with the Sun, the Moon, and the other members of the solar system. These features ensure that Earth remains a planet of rhythms and cycles, with predictable patterns of light, heat, and seasons. From the regular passage of days and nights to the long-term cycles of climate change, Earth's orbit and tilt define its character as a planet and its place in the vast expanse of space. Viewed from space, Earth's oceans and atmosphere are inextricably linked, forming a dynamic system that regulates the planet's temperature, climate, and surface conditions. This interplay between water and air is one of Earth's defining characteristics, influencing its appearance, stability, and evolution as a planetary body. Together, the oceans and atmosphere work to distribute solar energy, absorb and store carbon, and drive the complex cycles that shape the planet's surface. The oceans, which cover approximately 71% of Earth's surface, act as a massive reservoir of heat and energy. Water has a high heat capacity, meaning it can absorb and retain significant amounts of heat without dramatic temperature changes. This property allows the oceans to moderate Earth's climate, absorbing excess heat during warmer periods and releasing it during cooler times, a period ranging from more traditional summer to summer moderate and then cooler again. Ocean currents, driven by wind, temperature gradients, and the rotation of the planet, redistribute this heat around the globe, creating patterns such as the Gulf Stream, which transports warm water from the tropics to the North Atlantic. The atmosphere, a relatively thin layer of gases enveloping Earth, plays a complementary role, composed primarily of nitrogen, 78%, and oxygen, 21%, along with trace amounts of greenhouse gases like carbon dioxide and water vapor. The atmosphere traps heat through the greenhouse effect, and the atmosphere retains some of this heat, preventing Earth from becoming too cold. At the same time, the atmosphere circulates air masses, driven by the uneven heating of Earth's surface by the sun, creating wind patterns and weather systems. The interaction between the oceans and atmosphere is most apparent in the water cycle, a continuous process of evaporation, condensation, and precipitation. Solar energy heats the surface of the oceans, causing water to evaporate and rise into the atmosphere. As the water vapor cools, it condenses into clouds and eventually falls back to the surface as precipitation, replenishing the oceans, rivers, and lakes. This cycle not only regulates Earth's temperature, but also distributes fresh water across the planet, shaping its landscapes and ecosystems. Ocean-atmosphere coupling drives many of the planet's most significant weather patterns and climate phenomena. For instance, the El Niño Southern Oscillation, NESO, is a periodic warming or cooling of surface waters in the tropical Pacific Ocean, which affects atmospheric circulation. During an El Niño event, warm water disrupts normal wind patterns, leading to changes in precipitation, droughts, and storms across the globe. These interactions demonstrate the global reach of ocean-atmosphere dynamics and their profound impact on Earth's climate. From space, the movement of clouds over the oceans and continents is a striking visual representation of this interaction. Satellites capture the swirling patterns of hurricanes, the steady march of storm systems, and the gentle flow of trade winds across vast expanses of water. These atmospheric phenomena are closely tied to the energy exchanged between the oceans and the atmosphere, highlighting the interconnectedness of Earth's systems. The oceans also play a crucial role in regulating atmospheric composition, particularly through their ability to absorb carbon dioxide. Waves and currents draw CO2 from the atmosphere into the surface waters, where it dissolves and reacts with seawater to form bicarbonate and carbonate ions. This process, known as the oceanic carbon sink, helps moderate the concentration of greenhouse gases in the atmosphere, stabilizing Earth's climate over long timescales. However, the increasing levels of CO2 in recent decades have led to ocean acidification, a chemical shift that threatens marine ecosystems. The exchange of energy and gases between the oceans and atmosphere is not limited to Earth's surface. Deep ocean currents, driven by differences in temperature and salinity, circulate on timescales of centuries, transporting heat and nutrients around the planet. This process, known as thermohaline circulation, interacts with the atmosphere to influence long-term climate patterns. The relation between the number of people on Earth and the density of society has been represented by correlations. The melting of polar ice, driven by global warming, has begun to disrupt this circulation, with potential consequences for climate stability. Earth's rotation and axial tilt also influence ocean-atmosphere interactions. The Coriolis effect, a result of Earth's rotation, causes moving air and water to curve, creating distinct wind patterns such as the trade winds and westerlies. These winds, in turn, drive Earth's tilt and shape weather systems, leading to variations in weather and climate throughout the year. In the summer months, it is common for fortunes to trade to the polar oceans and western seasons, leading to variations in weather and climate throughout the year. Unlike other planets, Earth's oceans and atmosphere form a self-regulating system. Venus, with its thick atmosphere of carbon dioxide, lacks liquid water to moderate its greenhouse effect, resulting in surface temperatures hot enough to melt lead. Mars, with its thin atmosphere and limited water, cannot sustain a stable climate. Earth's balance of water and air is unique, creating a planet with dynamic weather, a temperate climate, and the ability to adapt to changing conditions over time. The interaction between Earth's oceans and atmosphere is a cornerstone of the planet's identity. It regulates the distribution of solar energy, moderates climate extremes, and sustains the cycles that define Earth's surface. This coupling is a testament to the planet's complexity and adaptability, marking it as a vibrant and evolving world within the solar system. The carbon cycle is one of Earth's most essential systems, regulating the balance of carbon between the atmosphere, oceans, rocks, and the planet's interior. This intricate cycle not only stabilizes Earth's climate, but also influences its geology and atmospheric composition over billions of years. Unlike other planets in the solar system, Earth's active carbon cycle is a testament to its dynamic systems and self-regulating capabilities as a planetary body. Carbon on Earth exists in multiple reservoirs: the atmosphere, where it is primarily found as carbon dioxide, CO2; the oceans, where it dissolves in water and forms carbonate compounds; the biosphere, as part of living organisms; and the lithosphere, stored in rocks, sediments, and fossil fuels. The movement of carbon between these reservoirs occurs on timescales ranging from days to millions of years, creating a dynamic balance that impacts every aspect of Earth's environment. One of the primary sources of atmospheric carbon dioxide is volcanic activity. When magma rises to the surface, it releases CO2 trapped within the mantle into the atmosphere. This process has been a significant contributor to Earth's atmosphere since its formation, providing the carbon necessary to sustain the cycle. At the same time, weathering of rocks on Earth's surface acts as a counterbalance, drawing CO2 out of the atmosphere. Rainwater, slightly acidic due to dissolved CO2, reacts with silicate rocks, breaking them down and forming bicarbonates. These bicarbonates are carried by rivers to the oceans, where they are used by marine organisms to build shells and skeletons. In the oceans, the carbon cycle takes on another layer of complexity. Dissolved CO2 interacts with seawater to form carbonic acid, which then dissociates into bicarbonate and carbonate ions. These compounds play a crucial role in ocean chemistry and are used by organisms like corals, mollusks, and plankton to create calcium carbonate structures. When these organisms die, their remains sink to the ocean floor, forming sediments that eventually become limestone and other carbonate rocks, effectively storing carbon for millions of years. A development known abduction zones, where tectonic plates converge, are another critical component of the carbon cycle. As carbonate rocks are drawn into Earth's mantle through plate tectonics, they are subjected to intense heat and pressure, releasing CO2 back into the atmosphere through volcanic eruptions. This recycling of carbon between the surface and the interior maintains a long-term balance, preventing the buildup or depletion of atmospheric CO2 over geological timescales. The carbon cycle also has a significant impact on Earth's climate. Carbon dioxide is a greenhouse gas, trapping heat in the atmosphere and moderating surface temperatures. Variations in the amount of CO2 in the atmosphere, whether due to volcanic activity, weathering, or human influences, can lead to changes in global climate. During periods of intense volcanic activity or reduced weathering, higher levels of CO2 have contributed to warmer climates, while increased weathering during mountain-building events has drawn down CO2, leading to cooler conditions and even ice ages. From space, the effects of the carbon cycle are not directly visible, but its influence can be inferred through observations of Earth's surface and atmosphere. The distribution of forests, oceans, and ice caps, as well as the composition of the atmosphere, reflects the ongoing processes of carbon exchange. Satellites, equipped with sensors for Marshmallow taxonomy, provide insights into how the carbon cycle is responding to natural and human-driven changes. Earth's carbon cycle is unique among the rocky planets. Venus, with its thick atmosphere of CO2, lacks processes to sequester carbon in rocks, leading to a runaway greenhouse effect and surface temperatures that exceed 450 degrees Celsius. Mars, on the other hand, has lost most of its atmosphere and water, leaving its carbon largely trapped in surface rocks and polar ice caps. Earth's balance of carbon storage and recycling, driven by tectonic activity, ocean chemistry, and biological processes, sets it apart as a dynamic and resilient planet. However, the carbon cycle is not immune to disruption. Human activities, particularly the burning of fossil fuels and deforestation, have significantly increased atmospheric CO2 levels in recent centuries. This imbalance has accelerated global warming, highlighting the delicate equilibrium that governs the carbon cycle. While the natural processes of weathering and ocean absorption can mitigate some of these effects, they operate on much longer timescales than the current rate of human-driven emissions. The carbon cycle's ability to regulate itself over billions of years underscores Earth's adaptability as a planetary system. By cycling carbon between the atmosphere, oceans, and interior, Earth has maintained conditions that are neither too hot nor too cold, avoiding the extremes seen on its planetary neighbors. This balance is a testament to the planet's dynamic processes and its capacity for long-term stability. The carbon cycle is one of the defining features of Earth's identity as a living, breathing planet. It connects the deep interior with the surface, the oceans with the atmosphere, and the geological with the chemical. From the slow formation of carbonate rocks to the rapid exchange of CO2 in the atmosphere, the carbon cycle is a cornerstone of Earth's resilience and adaptability, ensuring that the planet remains a vibrant and evolving member of the solar system. As a planet within the solar system, Earth occupies a unique and influential position. Its size, composition, gravitational influence, and location in the Sun's habitable zone have shaped its interactions with neighboring celestial bodies and its role in the larger cosmic environment. Earth is not an isolated object. It is part of a complex gravitational ballet that connects all planets, moons, and smaller objects in the solar system. Earth is the largest of the inner rocky planets, with a diameter of approximately 12742 kilometers, 7,918 miles, and a mass that significantly exceeds those of Mercury, Venus, and Mars. Its size and gravity are sufficient to retain a thick atmosphere and moderate surface temperatures, distinguishing it from its smaller neighbors, such as the Moon and Mars. This combination of size and location has allowed Earth to maintain liquid water, a defining feature of its identity as a planetary body. Earth resides in the Sun's habitable zone, the region around a star where conditions are suitable for liquid water to exist on a planet's surface. This location is not only ideal for water retention, but also provides Earth with a stable energy source from the Sun. The Sun's relatively constant energy output as a G-type main sequence star has allowed Earth to sustain a moderate climate over billions of years, avoiding the extremes of runaway heating seen on Venus or the freezing conditions on Mars. Gravitationally, Earth plays a significant role in the solar system's dynamics. Its mass influences the orbits of smaller bodies, such as the Moon, asteroids, and even artificial satellites. Earth's gravitational pull has helped to shape the trajectory of nearby objects, protecting the planet from potential collisions and contributing to the structure of the asteroid belt. Additionally, Earth's gravitational interactions with other planets, particularly Venus and Jupiter, have influenced its orbit and axial tilt over time, ensuring long-term stability. Earth's gravitational influence extends to its relationship with the Moon, the planet's only natural satellite. The Earth-Moon system is unique in the solar system due to the relatively large size of the Moon compared to Earth. This close relationship stabilizes Earth's axial tilt, creating predictable seasonal cycles and a stable climate. The Moon's gravitational pull also generates tides, which have played a role in shaping Earth's coastlines and influencing its ocean currents. The planet's position in the inner solar system places it in a region where terrestrial planets dominate, in contrast to the outer solar system's gas giants. Earth shares this region with Mercury, Venus, and Mars, each of which has a distinct composition and history. Comparatively, Earth's size and active geology set it apart, as it remains tectonically active and geologically youthful, while Mercury and Mars have long since cooled and solidified. Earth's relationship with the larger planets, particularly Jupiter, is also critical. Jupiter's immense gravity acts as a shield, diverting or capturing comets and asteroids that might otherwise pose a threat to Earth. However, this same influence can occasionally direct debris toward the inner solar system, contributing to periods of heavy bombardment in Earth's history. This dynamic interplay has shaped Earth's surface and played a role in delivering key materials, such as water and organics, during the planet's early formation. From a space perspective, Earth's interactions with the Sun are particularly striking. The planet's nearly circular orbit ensures a stable distance from the Sun, minimizing fluctuations in solar energy. Earth's magnetic field, generated by its molten iron core, creates a protective shield that deflects solar wind and cosmic radiation. This interaction between Earth's magnetic field and the Sun's energy drives phenomena like the auroras, visible near the poles, and influences the behavior of Earth's atmosphere and climate. Earth's role as part of the solar system extends beyond its physical interactions. The planet serves as a reference point for understanding other celestial bodies. Observations of Earth's geology, atmosphere, and climate provide insights into the processes that shape planets across the galaxy. Comparative studies with Venus and Mars, for example, highlight the importance of factors such as atmospheric composition, magnetic protection, and tectonic activity in determining a planet's habitability. While Earth benefits from its position and relationships within the solar system, it is not immune to external influences. The gravitational pull of other planets, particularly during alignments or close approaches, can subtly alter Earth's orbit and rotation over long timescales. Additionally, Earth remains vulnerable to impacts from asteroids and comets, though its position within a relatively stable region of the solar system minimizes these risks. Earth's unique role in the solar system is a product of its size, location, and interactions with other celestial bodies. It is both a participant in and a product of the complex gravitational dynamics that define the solar system's structure. From stabilizing its orbit to influencing the trajectories of nearby objects, Earth's presence is deeply intertwined with the behavior of the planets, moons, and smaller objects that share this cosmic neighborhood. In the context of the solar system, Earth stands out as a dynamic and evolving world. Its position in the habitable zone, gravitational relationships, and active geological processes set it apart from its rocky neighbors and establish its role as a vibrant participant in the intricate mechanics of the solar system. Earth's history spans over 4.5 billion years, a journey shaped by powerful forces both internal and external. In its earliest days, Earth was a searing, molten sphere, glowing from the heat of accretion, radioactive decay, and relentless collisions with planetesimals. This fiery beginning allowed the planet to differentiate into layers, with heavy elements like iron and nickel sinking to form the core, while lighter silicates rose to create the mantle and crust. This internal structure became the foundation for Earth's magnetic field, tectonic activity, and its long-term stability as a planetary body. During its formative years, Earth endured constant bombardment from asteroids and comets. This period, known as the Late Heavy Bombardment, reshaped the planet's surface repeatedly, leaving behind craters and scars. It was during this chaotic time that essential materials, including water and volatile compounds, were delivered to Earth, seeding the planet with the ingredients needed for its transformation into a water-rich world. These impacts, though violent, played a crucial role in shaping Earth's character as a dynamic and evolving planet. Around 4.5 billion years ago, Earth experienced one of the most significant events in its history, the collision with a Mars-sized body known as Theia. The impact ejected a massive amount of debris into space, which eventually coalesced to form the Moon. This event not only created Earth's natural satellite, but also profoundly influenced the planet's evolution. The Moon's gravitational pull stabilized Earth's axial tilt, giving rise to predictable seasons, and its influence slowed Earth's rotation over time, lengthening the planet's days from just a few hours to the 24-hour cycle we know today. As Earth cooled, its molten surface began to solidify, forming a fragile crust. This early crust was thin and unstable, frequently recycled back into the mantle by intense volcanic activity and impacts. Over millions of years, the crust thickened and became more stable, setting the stage for the development of continents and ocean basins. Volcanic eruptions released gases trapped within Earth's interior, creating a secondary atmosphere rich in carbon dioxide, water vapor, and nitrogen. This atmosphere, while harsh and unbreathable, was a precursor to the one we know today, and played a vital role in regulating the planet's temperature. Earth's surface remained volatile for billions of years, with tectonic forces driving the formation and breakup of supercontinents. These massive landmasses, such as Rodinia, Pannotia, and Pangaea, formed and fragmented in cycles lasting hundreds of millions of years. The movement of tectonic plates reshaped Earth's surface repeatedly, forming mountain ranges, ocean basins, and rift valleys. This constant renewal ensured that Earth's surface remained geologically active, unlike the ancient, static landscapes of Mars or Mercury. The planet's evolving surface was closely tied to its internal dynamics. Heat from Earth's core drove convection currents in the mantle, powering the movement of tectonic plates and fueling volcanic eruptions. These processes not only shaped the surface, but also played a crucial role in the carbon cycle, recycling carbon between the atmosphere, oceans, and interior. This long-term carbon regulation helped to stabilize Earth's climate, preventing extremes that could have rendered the planet uninhabitable. From space, Earth's evolution is evident in its vibrant and dynamic features. The planet's continents, arranged like pieces of a shifting puzzle, tell the story of billions of years of tectonic activity. Ocean basins, with their mid-ocean ridges and deep trenches, highlight the ongoing processes of seafloor spreading and subduction. Even the polar ice caps, a more recent feature in Earth's history, reflect the planet's ability to adapt to changes in climate and energy balance. Over time, Earth's geological activity began to decline, though it remains one of the most tectonically active planets in the solar system. Its core continues to generate heat, driving mantle convection and maintaining the magnetic field that shields the planet from solar wind and cosmic radiation. This magnetic protection has been essential in preserving Earth's atmosphere and surface conditions over billions of years. Earth's evolution has been marked by periods of intense transformation and relative stability. From its molten beginnings to its current state as a vibrant, water-rich world, The planet's journey is a testament to the interplay of internal and external forces. Viewed from space, Earth stands as a dynamic and ever-changing planet, its surface and systems shaped by a history that stretches back to the very formation of the solar system. As stable and enduring as Earth seems, its position and role in the solar system are not permanent. Over the coming billions of years, Earth will face dramatic changes, driven by the evolving Sun, the planet's own internal dynamics, and interactions with the wider solar system. While Earth's systems have proven resilient over its history, the planet's future is ultimately tied to the life cycle of the Sun, making its long-term fate inevitable. The Sun, like all stars, is undergoing a slow but inevitable transformation. Currently in its main sequence phase, the Sun is steadily fusing hydrogen into helium in its core. Over time, this process causes the Sun to brighten, increasing the amount of energy it emits. Within the next billion years, the Sun's luminosity will increase by about 10%, raising Earth's surface temperatures. This gradual warming will have profound effects on the planet's climate and ecosystem. As temperatures rise, Earth's oceans will begin to evaporate. Increased evaporation will inject more water vapor into the atmosphere, amplifying the greenhouse effect and accelerating warming. Eventually, the oceans will boil away entirely, leaving Earth as a dry, barren world. The loss of water will also affect the atmosphere, as water vapor is a significant component. Without the oceans and the moderating effects of water, Earth's surface temperatures will become extreme, resembling the current conditions on Venus. Over billions of years, Earth's core will continue to cool, reducing the convection currents that generate the planet's magnetic field. Without a strong magnetic field, Earth will lose much of its protection from solar wind and cosmic radiation. The solar wind will strip away the atmosphere more rapidly, further diminishing the planet's ability to retain heat and moderate surface conditions. This process has already occurred on Mars, which lacks a global magnetic field and has lost much of its atmosphere. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and enter the red giant phase. During this stage, the Sun will expand dramatically, engulfing the inner planets and radiating intense heat. While it is uncertain whether Earth will be swallowed by the expanding Sun or pushed into a more distant orbit, the planet's surface will be scorched and its atmosphere will be completely stripped away. If Earth survives, it will exist as a barren, rocky remnant orbiting the dying Sun. Earth's orbit is not entirely isolated. Gravitational interactions with other planets, particularly Jupiter and Venus, could cause slight changes in Earth's trajectory over billions of years. These interactions, though minor, may influence Earth's stability and distance from the Sun. During the Sun's red giant phase, these gravitational shifts could determine whether Earth is engulfed or spared, though in either case the planet will be rendered uninhabitable. Earth's internal heat, driven by the decay of radioactive elements and residual heat from its formation, will continue to diminish over time. As the mantle cools, tectonic activity will slow and eventually cease. Without tectonics, Earth will lose its ability to recycle carbon dioxide through the carbon cycle. The planet's surface will become static, resembling the geologically inactive surfaces of Mars or Mercury. Beyond the Sun's life cycle, Earth's fate will also be influenced by the evolution of the solar system. The orbits of the planets are not entirely stable over immense timescales, and interactions between the outer planets, asteroids, and comets could lead to additional impacts on Earth. While these events are unlikely to significantly alter Earth's trajectory, they could further contribute to the planet's eventual decline. When the Sun completes its red giant phase, it will shed its outer layers and collapse into a white dwarf, a dense remnant of its former self. At this stage, the solar system will be a shadow of its current state, with most of the inner planets destroyed or rendered lifeless. If Earth survives the red giant phase, it will orbit the white dwarf as a frozen, airless world, its surface scarred by billions of years of cosmic and solar evolution. Earth's future shares similarities with other terrestrial planets. Venus, for instance, is already experiencing conditions that may mirror Earth's distant future, with a runaway greenhouse effect and a dense, inhospitable atmosphere. Mars, on the other hand, has already cooled and lost its magnetic field, offering a glimpse of Earth's fate as its interior cools. These planetary comparisons highlight the inevitable stages of terrestrial planet evolution within a changing solar system. From a cosmic viewpoint, Earth's future is part of the natural life cycle of stars and planets. While the planet's systems and features have made it resilient for billions of years, its eventual decline is a reminder of the finite nature of planetary stability in an evolving solar system. Earth's ultimate fate, whether as a vaporized remnant or a frozen, barren rock, is a testament to the powerful forces that govern the universe and the impermanence of even the most stable planetary systems. Seen from the vast emptiness of space, Earth is a remarkable sight. Its vibrant blue oceans, swirling white clouds, and diverse landmasses stand out as a beacon of dynamic processes in a solar system dominated by barren, rocky worlds and gas giants. This perspective reveals Earth not just as a planet, but as a living, evolving system, shaped by interactions between its atmosphere, oceans, and solid surface. From space, the first feature that captures attention is Earth's deep blue color, a result of sunlight scattering through its oceans. These oceans, covering more than 2/3 of the planet's surface, play a vital role in regulating its temperature, absorbing solar energy, and distributing heat through currents that span the globe. The oceans reflect and refract light in a way that makes Earth unique among the planets, creating a vivid and dynamic appearance. Hovering above the surface, the planet's atmosphere forms a thin yet protective shell. Layers of gases scatter sunlight, producing the bright glow of a blue sky when viewed from within, and a delicate haze when seen from orbit. The atmosphere's dynamic nature is evident in the movement of clouds, shaped by wind patterns and influenced by Earth's rotation. Hovering above the surface, the blue planet has many encounters, often suited for winter. These clouds reflect sunlight, moderate temperatures, and contribute to the water cycle, linking the atmosphere and oceans in a seamless interplay. The landmasses, though occupying a smaller portion of the surface, are equally striking from space. Their varied colors, greens, browns, and whites, indicate forests, deserts, and ice caps respectively. The shapes of continents hint at the slow but constant movement of tectonic plates over millions of years. Mountains rise prominently, casting long shadows at sunrise and sunset, while river systems and deltas reveal the ongoing erosion and sedimentation that shape the planet's surface. Even volcanic eruptions, though destructive locally, contribute to Earth's dynamic geology, with plumes visible from orbit. One of Earth's most fascinating features, as observed from space, is the terminator line, the dividing boundary between day and night. As the planet rotates, this line moves across the surface, bringing the daily rhythm of sunrise and sunset to every corner of the globe. The terminator line is not static, but varies slightly due to the tilt of Earth's axis, creating the changing patterns of light and shadow that define the seasons. In my book, Earth's magnetic field, invisible to the naked eye, is another feature that sets it apart. This field extends into space, forming the magnetosphere, which protects the planet from harmful solar and cosmic radiation. When solar wind particles interact with the magnetic field near the poles, they create auroras, breathtaking displays of light that shimmer in greens, reds, and purples. These natural spectacles are a visible reminder of the powerful forces shaping Earth's environment. From space, Earth's uniqueness becomes even more apparent when compared to its neighbors. Venus, shrouded in thick clouds of sulfuric acid, reflects sunlight so brightly that it appears featureless, with no evidence of oceans or dynamic weather systems. Mars, with its red, dusty surface and thin atmosphere, appears cold and static, its once active systems long dormant. In contrast, Earth is alive with motion. Clouds swirl in endless cycles, oceans churn with waves and currents, and even the solid surface changes through tectonic activity and erosion. Earth's position in the solar system further emphasizes its singular nature. Orbiting within the habitable zone, it receives just enough solar energy to sustain liquid water without boiling it away or freezing it entirely. The balance between incoming solar radiation and outgoing heat is maintained by Earth's atmosphere, a delicate equilibrium that is evident in its rocky neighbors and lack of extreme climate swings compared to its rocky neighbors. After an encounter with an Earth's atmosphere, it is possible to surmise that since the location of Earth's, this only two traits within solar system, compared to its rocky neighbors, have maintained some sense of separation from the rest of the universe, it is likely to drive its own self. Artificial satellites and spacecraft, circling Earth at various altitudes, provide continuous views of the planet. From their vantage points, they monitor the movement of hurricanes, the retreat of glaciers, and the flow of ocean currents. These observations reveal Earth's dynamic systems in real time, allowing us to study the planet's processes and understand how they interact on a global scale. The view from space underscores the interconnectedness of Earth's systems, as changes in one region often have cascading effects across the planet. Earth's moon, visible in orbit as a gray, cratered companion, adds to the perspective of Earth as a system within the solar system. The moon's gravitational influence on Earth creates tides, stabilizes the planet's axial tilt, and contributes to the rhythms that define its environment. Together, Earth and the moon form a unique planetary system, interconnected and mutually influential. In the vast expanse of the cosmos, Earth stands out not just for its vibrant colors and dynamic systems, but also for its balance. It is a planet shaped by cosmic forces, internal geology, and atmospheric processes, all working together to create a world unlike any other we know. Seen from space, Earth is a reminder of the intricate interplay of forces that define its character, a singular perspective that highlights its place as a remarkable object in the solar system.